Have you ever came across derivatives and you've seen these words where they are telling you do not simplify? So today we're going to be doing a couple of examples, and I will also be unpacking how you go about analyzing your derivatives and getting to your final answer. So let's start with um, example one. So we're going to be doing a lot of examples also. So let's say we have a root of t. They've given you a root of t and they've told you to derive it, and you shouldn't simplify the answer. So the first step that you ask yourself is that, okay, I do have my root of t. Do I have any other rule in derivatives that tells me specifically to deal with square roots? Then you'll realize that actually there isn't. Now the second step is to try and rewrite whatever that you are given. We know root of t can be rewritten as your t to the exponent 1 over 2. You see, so now you ask yourself again that do we have any rule that guides us against this one? Then we know, okay, we have the rule that says when we have our derivative dy over dx of your x to the exponent n, we can write this as your n multiplied by your x to the exponent n minus 1. See, so now you know, okay, I'm going to apply that specific rule to whatever that I have here. So it means now you can see what you're going to drop that 1 over 2 down, then you're going to be having t. Then we know 1 over 2 minus 1 is going to give us minus 1 over 2. And that's simply how you're going to leave your answer, because we are not going to be simplifying. You're going to be ending here. So if you were to simplify, simplifying means now you were going to write this answer as your 1 over 2 root of t. So this is your simplified version. So if they tell you do not simplify, you're mainly going to be writing up to that point. So if it's 2 mark, you'll be getting those marks there. Then now let's look at another example. So this would be the part where it's simplified. So let's look at another example. So now let's just say they've given you something like your 2 minus 3x to the exponent 4. See, so if you are given this, you ask yourself again, what type of rule do I have for a situation where I have, I would say, your x to the exponent 4, or your function raised to the exponent. So basically just give out the rule. So we know that we still have a similar rule, but now we're going to be looking for a rule that also lets us differentiate what's internal, because we know we can also do differentiation in terms of your chain rule. So it's one thing that you have to be careful that, okay, when you are differentiating, am I still going to be differentiating the internal side or what? Because the differentiation for this and for this one, it's completely different. So I'm just going to explain now that, okay, for this one, which rule are you going to use? You have your dy over dx. We know we have x to the exponent n, then we have n multiplied by x to the exponent n minus 1. But for this one, we're having something which is similar. But I want you to notice that, okay, we still have the internal part that would be left if we try to use this formula. Hence, we're going to be using the formula from the chain rule. So what does the formula from the chain rule says about this one? So the formula for the chain rule says if you are differentiating dy over dx, then you have you have your f of x to the exponent n, then you can say you have your n, you have your f of x, then you're going to say you have n minus 1 multiplied by the derivative of what's inside, because on this one you have some terms that are on the internal side, but here you see you don't have any term that's inside, so hence that's why on this one we're using the chain rule, and on this one we're just using this one, which is straightforward. So it now means we're going to be using the chain rule on this one. So I just hope this explanation does make sense on why we're using this one, and also this type of example. So we have this, so it means now if we're using this, we're going to be bringing the 4 down, then we will have our 2 minus 3x, then we have 4 minus 1, we will have 4, then we multiply by whatever that is going to be internally. So what's going to be left? To the derivative of 2 minus 3x, we're only going to be left with minus 3. See, so that would be that. Then this one, yeah, you're just going to leave it in this state. See? So we're going to leave it in this state. So now we're going to be looking at another example. So I'm going to be giving you guys another example. So another example that I would have, it's what, okay, let's just use one for ln. So we know we have ln of, let me just say cos of t. So once again you will ask yourself that, okay, which rule am I going to use in this instance? You see, then you'll know that, okay, if you dig in your rules, you have your rule for ln, which says if you're differentiating your dy over dx, then you have your ln of f of x. So you're going to be having your derivative of what's inside over your f of x over, or what's inside. So if we're looking at this, that okay, when it comes to this one, what's inside is cos of t. Then we know if we're differentiating our dy over dx, if we're differentiating cos of x, what are we getting? We know that if we're differentiating cos of x, we always get our minus sine of x. See, so it means now we're going to be having what? We're going to be having minus sine of t. Remember here I'm just giving them in x because that's how you would normally find it. You'll find the rules in your standard form. But remember, we're working it in t's here. Here we're working in x. So you always write in whatever that you're having. Then you divide by the original of what's inside, which is what? Which is still going to be your cos of t. So now it means you can just simply go and write your final answer, that you will have your minus sine of t divided by your cos of t. So you simply know that, okay, with that one I'm done. I have to continue and do another one. So I'm just trying to think of one that could be a little bit different from what we have this side. So okay, let me just use a case where I have some sort of like an exponential function. So let's just say now we are given something like your 4 to the exponent of 1 minus x. So you ask yourself, which type of rule is there for me when I have something like my a to the exponent f of x? You see, so we do have a differentiation rule that says when you have your dy over dx of your a to the exponent f of x, what do you have? We are having this because there is also another rule that says you have your dy over dx, but in this instance, what do you have? You have your a to the exponent x. You see, in this instance, we're having a function here. Here we're not having a function, so you will see that that's why you need to be careful with these types of questions. Here you have your ln of a multiplied by a to the exponent multiplied by a to the exponent x. But for the one where you have a function, you will have your ln of a multiplied by your a to the exponent x multiplied by your derivative of your function. You see, so these are two rules that are there. You have to check that, okay, with this one is when I just have a constant, but this one, it's when I have a function at the top. And if you check this one, this is a function, it's a linear function, so it means now you're going to have to use this rule that you see that side. So it means what's going to be your answer for that one? You're going to say you have, let me use a black mark, you have your ln of 4 multiplied by your 4 to the exponent 1. Let me see, did I write it correctly there? Oh, okay, this is not this one, this is f of x. This is still f of x, so apologies for that one. Then I'm only noticing it because I have to write this one. You have 1 minus x, then you have to differentiate this 1, which is the f of x, the internal part. Then here you're going to be having what? You're going to be having minus 1. Because sometimes I also get students that ask, why did you use this rule in terms of this rule? Or you get students that are using this rule. So I hope now you know the difference, that okay, if I have a function at the top, I'm going to be using this one. If I don't have a function, I just have a constant, then I'm going to be using this rule. So I just hope that clears the confusion. So okay, so we're going to be focusing on another one. So okay, so let me just give you guys another one, that okay, we have something like your cos of 4t. Then I'm going to be writing two differentiation rule that you are going to use. We have the normal differentiation rule, and we have the differentiation rule in terms of chain rule. So they would give you the rule that okay, you have the first rule that says you have your dy over dx for cos of x, which just gives you what? It gives you minus sine of x. But you have the second one, which says your dy over dx of cos of f of x. This is the same as having what? This is the same as having your minus sine of f of x multiplied by the derivative of your f of x, by the derivative of your f of x. Now you go and check again, or you can pause and ask yourself, which rule are you going to use between the two, and also why. Then okay, you will see that okay, for this one, this is mainly the one where I will be using a constant. And once again, this is the one where I will be having a function. What do I mean by a function? We're having your cos of f of x. Your f of x gives you a function. In this one, we just have a constant. So let me just do it like this so that you can notice the difference. Here, do I have a constant or a function? I definitely have a function. So it means now I'm going to be using this rule. See, so don't let that one confuse you. So it means if I'm going to be finding the derivative for this one, what am I going to have? It means I'm going to be having, let me use a black one. I'm going to be having minus sine of 40, because I'm following this one, multiplied by what? By the derivative of what's inside. The derivative of 40 will give you what? Will give you 4. You see? So that's basically how you go about solving those ones. So that would be correct for this, correct for this, correct for that. So as you are busy doing them, you can just like write these functions down, but the more you practice this, the more you'll be able to remember that, okay, here I'm going to be using my chain rule, or here I'm going to be using the normal derivative rules, you see. So I think I'm just gonna erase these ones and we can focus on more examples so that you guys get comfortable. Okay, so let's see which example can we think of. I'm looking for something that we haven't done before. Okay, we can even try to do it in a more much complicated way. That, okay, we will have something like your cos of what? Your cos in brackets, we have something like your 5t. Then you still ask yourself, we remember the last rules that we had. We had the rule for a function and we had the rule for a constant. For this one, you know, your 5 to the exponent t, it's definitely a function. So it means we're going to be using your dy over dx, where you are having cos of f of x. This will give you minus sine of f of x multiplied by the derivative of f of x. See? So we're going to be starting with those. We start by, okay, seeing what are we going to have. We're going to be deriving this one, and we'll say the cos, we will say we have minus sine of what? Sine of sorry about that one. We have minus sine of 5 to the exponent t. Then we multiply by the derivative of what's inside. What's inside? It's your 5 to the exponent t. Then we have our 5 to the exponent t. Then we ask ourselves which rule is there for this one. We know for this one, the rule that we have, it's when we're having something like your a to the exponent x is equals to your ln of a multiplied by your a to the exponent x. So you notice in this instance here, we're only having a constant, which is t. We're not having a function. So hence, that's why I used this one, not the one where you're having your a to the exponent f of x. You see? So now it means if we're going to be deriving that, we're going to be getting what? We're going to be getting ln of 5 multiplied by your 5 to the exponent t, then your derivative for your t is 1. So you can even just like leave that one out. Then you're going to have your final answer that says this one. We're going to translate here. You have your ln of 5 multiplied by your 5 to the exponent t. So that would be the final answer for this type of question. So we're going to wrap out this explanation and working out, and we continue with more example. So now let's just say, what do we have in this instance? Now we have something like your, oh, let me just give your 5 to the exponent cos of t, because I'm just playing around this type of example, so you know, okay, if I have this, I do this, if I have this, I do this. Then you say, okay, what would be the first step? If I'm going to be differentiating this. Which rule am I going to use? Then you know, or definitely know, that I have my what? My a to the exponent f of x, because I have a function. And you know that, okay, this is part of your exponential functions. Then you know, for this type of one, you have your dy over dx, you have your a to the exponent f of x, which is your ln of a multiplied by your a to the exponent f of x multiplied by the derivative of what's on the internal side. You see? So how is that going to look like? You will say you have your ln of 5 multiplied by what? By your 5 to the exponent cos of t. Then and now you what? You differentiate what's internally, or that function. Then if you differentiate, we know if you're having your dy over dx of your cos of t, this will give you what? Your minus sine of t. See, so it means here we're going to be having that minus sine of t. Then here we'll say we have minus sine of t. So that would definitely be the final answer that you're getting. So I just hope now the flow with this thing is at least maybe getting there. You see. So let me see. I'm trying to come up with different examples. So okay, so let's just look at this one where you're having something like you have your sine into your 1 minus t to the exponent 5. Then they ask you to derive that, and you're not supposed to simplify. But with this one, I don't think you can even take them much further, so this would be finished in this instance. So first things first, you're going to ask yourself, which rule do I have that is for sine of f of x? Because this is definitely a function, so you know you're definitely dealing with what? Here you're dealing with something like your sine of f of x, because you're having a function inside. So you know the rule that you have your dy over dx, where you are having sine of f of x. What are they telling you? They tell you that for your sine of x, you will have your cos of f of x multiplied by what? By your differentiation of what's in and sine. So how is that going to look like? You will say, okay, I'm going to start and say I have my cos of 1 minus t to the exponent 5 multiplied by the derivative of what's inside. So the derivative of what's inside, what do I have? I have my 1 minus t to the exponent 5. So which differentiation rule am I going to use for this one? We're using the one where I have your x to the exponent n. And what does it say? It says if you have your dy over dx, you have your x to the exponent n. This is the same as having n multiplied by x to the exponent n minus 1. So it means I'm going to be having your 5t to the exponent 4, but it's going to be minus, because this one derivative of 1 will just be 0. So as I said, here you're going to be having that minus 5t. So you can come this side and say, okay, the derivative for that one is minus 5t to the exponent 4, and that would be the answer for this one. So you see how we go about doing these types of example. So it's just few things that you have to ask yourself before you can jump into the actual solution. Because if you can just like receive this and you are thinking about the first rule, whereas you have the second rule, you are more likely to do your mistake. Ask yourself that in this instance, I have sine and I also have this. Does this look like sine of x or sine of f of x, which is going to be a function inside? You see, I have my 5 to the exponent cos of t. Then I know this is the same as having your a to the exponent x, but now in this instance it's my a to the exponent f of x, because this one is it's a function. You see, then you come to this one, you would normally have your cos of x, but in this instance I have cos of f of x because this inside it's a function. Then you look for the applicable rule in your chain rules, because with us we're dealing with two rules. We have the differentiation formulas, then we also have the differentiation formulas in terms of the chain rule. So with the differentiation formulas we have about 7. Then with the differentiation formulas in terms of chain rule we have about 6. You see, so I think, yeah, I will also try to show them here within this video, because the proper thing was that I was supposed to have included them at the beginning of the video so that you guys can know exactly the rules that I'm referring to. But I will also just like include them in this time slot, then you can pause the video, check them out. Then I think we can do one last example after this. So let's just say now we have something. Okay, since I was just more focused on this, I can use a similar one. That, okay, what do we have? We have something like your, let's just say you have your 5 to the exponent x squared minus your 3x. Then they ask you to find the differentiation for this one. Then okay, you check this one, that okay, you know this one you would normally have which types of family. You have your a to the exponent you have your a to the exponent x, then you have your a to the exponent f of x. This would be your exponential where you have a constant. This is your exponential when you have a function at the top. So we definitely mean between these two that you're going to use this since you're having a function at the top. So for this second one, what do they say? They say, okay, if you have your dy over dx of a to the exponent f of x, this is the same as having your ln of a multiplied by your a to the exponent f of x multiplied by the derivative of what's inside. You see? So the quick thing to note, as usual, check if you're having a function anywhere. So if we're going to be applying that one, we're going to still say we have our ln of 5 multiplied by our 5 to the exponent x squared minus 3x. Then we differentiate by what's on the internal side. So what's going to be left? We're going to be left with your 2x minus 3. See? So we're going to say this side we have the 2x minus 3. It's going to be the derivative of what's internally, which is that part. So yeah, I think so far we've done a lot of examples on derivative. Then I can say now the one that would like to ask is the one that they would give you something like your e to the exponent t. Then if they say find the derivative of e to the exponent t, your derivative of your e to the exponent x is the same as your e to the exponent x. So it means here you're just going to come and say this would be e to the exponent t. It doesn't change. The only time when it will change it's when you are given a function. Like for instance, you have to derive your dy over dx. You have your e to the exponent f of x. So it's being raised to a function. You're going to still have your e to the exponent f of x, but now you will have to derive the function that you're seeing here. So it's going to be like that. See, so that's one thing that I also wanted to highlight. Then yeah, I think if you guys are looking for more examples, you'll just like let me know in the comments that yeah, you please do more examples or give us more examples. Then I'll just like attach a link with more examples for you guys, or yeah, you can just ask them directly on my number. So that's it on your differentiation. I will see you guys in another video.